So continuing to look at transformations of a logarithmic function. So we want to sketch the graph of y equals 2 log base 3 of negative x plus 1. And so like we saw yesterday, we would have to do a bit of work here. Our b value is negative 1, but to get the true value of h, b must be taken out as a common factor. So that's a step that we would probably want to do here. And when you take out a common factor of negative 1 there, you actually get x minus 1 inside the rounded brackets, which means we have an h value of positive 1, not negative 1. But this is a transformation of y equals log base 3 of x. This is a transformation of y equals log base 3 of x. So we want to get a table of values for this. And like we did yesterday, it's probably going to be easier to convert this from logarithmic to exponential. By starting with the base and cycling through, that'll be 3 to the y equals x. So when we do our table of values here, it's probably going to be easier once again to start with y values. When y is negative 2, 3 to the negative 2 will be 1 over 3 squared, or 1/9. That's our x value. When 3 is negative 1, 3 to the negative 1 is 1 over 3 to the positive 1, or 1/3. When y is 0, 3 to the 0 is 1, 3 to the 1 is 3, and 3 squared is 9. So these are the points on the original function y equals log base 3 of x. We just converted it from logarithmic to exponential so that it make it easier to get a table of values. And because the equation was x equals 3 to the y, we started with y values. So 1/9, comma, negative 2. 1/3, comma, negative 1. 1, comma, 0. 3, comma, 1, and 9, comma, 2. So like all our other graphs of logarithmic functions, the y-axis is a vertical asymptote. And we're going to transform that. We're going to transform it by applying our 3 parameters. The first thing we see is that we have an a value of positive 2. So that's going to cause a vertical stretch by 2. Then we have a b value of negative 1, which means it's going to reflect over the y-axis. And then we have an h value of positive 1, which is going to cause it to shift 1 right. So, like we did before, let's set up a table here. The original points come from y equals log base 3 of x. And our first transformation we'll do is using our A value being 2. So that's a vertical stretch by 2. We're going to multiply all the y values by 2. All the y values get multiplied by 2. Our next one was a b value of -1. We flex it over the y-axis, so all the x values will be multiplied by -1. And finally, an h value of 1 shifts the graph 1 to the right. So we're going to add 1 onto all of the x values. So we add 1 to all the x values to shift it 1 to the right. Okay, so we can plot these points on there. 0.89, which is just below 1, comma, -4. 2/3, comma, -2. 8/9 is just below 1. I drew it just higher than 1. Oh no, it's over here. We're good. So 2/3, comma, -2, 0, comma, 0, -2, comma, 2, and -8, comma, 4. So this graph, vertically stretched, which doesn't change its position, but it shifted 1 to the, it reflected over the x-axis, and also shifted 1 to the right. So because of that, our vertical asymptote shifted 1 to the right. It is at x equals 1. And so there's the graph of the transform function. So we've been using this process right from the start. When we have multiple transformations, we start with points on the original graph. And then we write the new points after each transformation to get the new graph. So some of the things we're asked to state. The first part is the equation of the asymptote. It's an equation, so it's got to have an equal sign in the variable. That's x equals 1. Part 2 asks us for the domain and the range. So the domain for this graph, remember when you use interval notation, it's always smallest to greatest. -infinity to +1, and neither are included. Our range hasn't changed. y-intercept. This graph does go through the y-axis, and actually this graph goes through the point 0, 0. So our y-intercept and our x-intercept are both the origin. So our table told us that, but you can also confirm that by letting x equals 0 in the equation. And if you let x equal 0, so let's do that below here. So we'll take the equation 2 times log base 3 of negative 0 plus 1. Negative 0 is still 0 plus 1 is 1. And to evaluate log base 3 of 1, that's asking 3 to what power is 1. It doesn't matter what the base is. No matter what the base is, if you want the answer to be 1, the exponent is 0. 3 to the 0 is 1. So algebraically, just as a check to confirm that we did everything correctly to get that point, there's our y-intercept. And so our x-intercept is at the same spot. And then part 5 is the mapping. So the part that changed the x values is we multiplied them by negative 1, so x becomes negative x, and then we added 1 onto it. The y values were simply multiplied by 2 for the vertical stretch. Right, so there's the mapping notation. Okay, this next example where we're given a graph, as it says on the screen, the red graph is generated by stretching the blue graph of y equals log base 4 of x. On your page it's not colored, but the original graph is labeled. First one is log base 4 of x. Write the equation that describes the red graph. So as we've seen before too, often there's going to be corresponding points that are given, right? And so we can use that to get our equation. So if we use these 2 points as the corresponding points, that would, if you look at it and compare them, you could say that it has been horizontally stretched, okay? Because a y value, an x value of 4 became an x value of 1. So from going from 4 to 1, you multiply, or you divide by 4, which is the same as multiplying by a quarter. So by comparing those 2 points and saying it has to be a horizontal stretch, it can't be a shift because both graphs have the same vertical asymptote, the y-axis. If the graph shifted to the left, that would shift as well. It didn't. So one way to do this is to say that there is a horizontal stretch by a quarter. And then remembering that when you have a horizontal stretch, the stretch factor and the b value are reciprocals of each other. So that would mean that b equals 4. The reciprocal of the horizontal stretch factor. And the equation would be y equals log base 4 of 4x. I do. Yes. There you go. Thank you very much. We could also do this by, again, recognizing that there is a horizontal stretch here, which means that we have a b parameter. This is a different way we could get the same answer. Recognizing that, again, it's a horizontal stretch, so that's our B parameter. And we can use that point, the point 1, 1, that red graph goes through. If the graph goes through that point must satisfy the equation. So you're going to have 1 equals log base 4 of B. And then to find out what B is, convert from logarithmic to exponential. Start with the base and cycle through. 4 to the 1 equals B. So B equals 4. So we did it by logic, realizing that there's a horizontal stretch of a quarter, so therefore the B value is 4. Then we also did it by using an algebraic approach. Again, recognizing that there has been a horizontal stretch here. But if you look at these two graphs, you might also say, well, couldn't there also be a vertical stretch going from this point here up to that point there? And the answer to that would be no, because that would also mean that that point there would vertically stretch to get the point above, but the y value there is 0. If you're vertically stretching a graph, you're multiplying all the y values by the stretch factor. The y value here at the x-intercept is 0. When you multiply it by anything, it wouldn't change. It'd be invariant. So you cannot say that the graph could also be found by doing a vertical stretch. Because if it did, the x-intercept would be invariant. Okay, so only the horizontal stretch works here. And as you can see, there's 2 ways to do it. So we can do the same thing for this one, going from the blue to the red. It's the same original graph. But now, when we look at the new one, I think it's obvious that the graph has been reflected over the x-axis, as well as a vertical stretch, because the distance from the x-axis to the corresponding point definitely changes. This point is 1 unit above the x-axis. Down here, we're 3 units below. So this should work if we reflect it over the x-axis and do a vertical stretch by 3. And we can do all those simultaneously by saying that a is negative 3. That'll cause a vertical stretch as well as reflect. So that would mean that my new equation would be y equals negative 3 log base 4 of x. So we did that just by using some logic. But as we saw above, we could also do it algebraically. If we recognize that the transformation here is vertical, a stretch and a reflection, and that means again that there's been an a parameter that's been introduced, we can find the value of a algebraically by subbing in the point, 4, negative 3. And log base 4 of 4 is 1. That's asking 4 to what power is 4? Another way of looking at it, log base 4 of 4 can be evaluated using the change of base identity. Log 4 over log 4. You're dividing something by itself, you'll get 1. Either way. So there's another reason why the value of a is negative 3. So again, we did this before, where we found an equation by using some logic, figuring out what the transformation is, and then changing the parameters, as well as doing it algebraically by using a point on the graph. but you still must recognize what parameter is being changed. Okay, welding is the most common way to permanently join metal parts together. Welders wear helmets fitted with a filter shade to protect their eyes from the intense light and radiation produced by a welding light. The filter shade number N is defined by that function, where T is the fraction of visible light that passes through the filter. Shade numbers range, so that's N, from 2 to 14, with a lens shade number 14 allowing the least amount of light to pass through. The correct filter shade depends on the type of welding. A shade number 12 is suggested for arc welding. What fraction of visible light, so you want to know what T is passed through the filter to the welder as a percent to the nearest 10,000th. So we want to find out what T is if N equals 12. We want to know what T is if N equals 12. So we're going to solve for T. And before we can do that, we need to get the log of T by itself. So I'll subtract the 1 on the right from both sides. So that'll give us 11 on the left equals 7 times negative log T all over 3. I can multiply by 3 and divide by 7. That's the same as dividing by 7/3. And dividing by 7/3 is the same as multiplying by the reciprocal. Multiply by 3, divide by 7. So I'll take the 11. I'll multiply it by 3 and divide by 7. So that gives us this decimal, 4.71, which I'm going to write down rounded, but I'm keeping it in my calculator. So 4.71 equals negative log T. And you know what? Maybe let's do it this way. Let's write it as a fraction in lowest terms. So I took the 11, I multiplied by 3 to get 33, and then divide by 7. So it'll be 33 over 7. That's better. We'll divide both sides by negative 1. And now we can solve for T. This is a common log, no base indicated, which means it's base 10. And we need that base because we're going to change it from logarithmic to exponential. We're going to start with the base and cycle through. 10 to the negative 33 on 7 will equal T. So this will give us the fraction of visible light that'll pass through that filter. If we work it out, it'll give us our answer as a decimal, 10 to the power negative 33 over 7. Quite small. The calculator gives it in scientific notation, 1.93 times 10 to the negative 5. So 0 point and then 4 zeros, followed by 19306, etc. So that's as a decimal. To change it to a percent, we multiply it by 100. And there's your answer as a percent, and we're asked to do that to the nearest 10,000th, which is 4 decimal places, 0.0019%. That's the percentage of visible light that passes through that filter. So again, there's that process of converting from one form to another. Going to have to do it lots. Bases are the same. Start with the base, cycle through. Did you know there is a logarithmic relationship between butterflies and flowers? In one study, scientists found that the relationship between the number F of flower species that a butterfly feeds on and the number B of butterflies observed can be modeled by that function. Predict the number of butterfly observations, which is what B is, in a region with 25 flower species. That would be F. So F is 25. We want to know what B is. So we'll get the log B by itself, and then that will allow us to get B by itself. So we'll add the 2.641 to both sides. So that'll be 27.641 on the left, equaling 8.958 log B. We'll divide both sides by 8.958. So 27.641 divided by 8.958. Approximately 3.09. So I'm going to round it to write it down, but I'm keeping that entire number in my calculator. That's what log B equals. And again, this is a common log, no base indicated, which means base 10. So if we're going to convert to exponential, we start with the base and cycle through. 10 to the power 3.09 will equal B, the number of butterflies in that region with 25 flower species. So 10 to the entire decimal that we just found, approximately 1,218 butterflies. She's constipated. Give her a break. That's true. Prune juice. Telling you. Hey, you're 3 watermelons. What? Sure. I used